Welcome to EDU World Space.
Okay, so we have an elevator at 3 different points here. So in the first one, so we have 1, 2, 3. In the first one, it is 10 meters up from the ground, or from the base. So our height here is 10 meters. And in the second, it is 100 meters up from the ground. So our height is 100 meters. And in the third part, it is compressing a spring at the very bottom. So it's fallen down to the bottom. There's a spring here. The spring is compressed some distance, call delta x, but our height is 0. So we want to answer some questions about the energy at these different points. So when it's not touching the spring, its potential energy is gravitational potential energy. So in part A, it asks about the potential energy relative to the ground. It doesn't actually say at what height, but in general, the potential energy relative to the ground, is our gravitational potential energy, is going to be mgh. So at any point, we can say that the potential energy is mgh. We just have to know what height. I think in this first part, they're actually just asking for the height in the first part. So when it's 10 meters up, so height 1. So our potential energy at that point is going to be, the mass here is 2,500 kilograms. So 2,500 kilograms times 9.8 meters per second squared for g, and then the height of 10 meters. And that's going to give 2.5 times 10 to the 5 joules. So this is our potential energy at that point. And then in part B, we are asked about the potential, or we're asked about the work done to raise the elevator car up to a height of 100 meters. So from 1 to 2, it's been raised a certain amount. So that's 100 minus 10 meters, right? So it goes from 10 to 100 meters, so 90 meters up. So the work done is just the work done against gravity here. So they say that there's no friction. So our work is just going to be mg times h2 minus h1. So we've lifted it up that height. So that's the work we put in. So that's 2,500 kilograms times 9.8 meters per second squared times 100 meters minus 10 meters. And that work is going to be 2.2 times 10 to the 6 joules. And then in part C, it asks about the potential energy in part 2 here. So when it's 100 meters up. So that's just going to be mgh2. So that's 2,500 kilograms times 9.8 meters per second squared times 100 meters. And that is going to be 2.5 times 10 to the 6 joules. So that's the potential energy at that point. Okay, and part D, they ask about the velocity of the elevator and the kinetic energy right before it hits the spring. So at that point, we consider the height to be 0. And we know that because of conservation of energy, the total energy at any of these points has to equal the total energy at any other point. So we can just take the energy at position 2. So when it is at rest at a height of 100 meters. So that was what we found in part C. So the total energy there is 2.5 times 10 to the 6 joules. And that was mgh2. So that was the total energy at that point. That's got to equal the total energy right before it hits the spring. So it's not compressing the spring yet, but we have just kinetic energy, which is equal to 1/2 mv squared. So our m's are going to cancel out here, mass. And we just want to find the velocity. So let's multiply both sides by 2 and take the square root to get that the velocity right before it hits the spring is going to be 2g h2. So that is going to be 2 times 9.8 meters per second squared times 100 meters. We take the square root of that, and we get a velocity of about 44.3 meters per second. So the kinetic energy here is just going to be 1/2 mv squared. And now we have our velocity, we can plug that in. So 1/2 times 2,500 kilograms times 44.3 meters per second squared. And that is going to give us a total energy of 2.5 times 10 to the 6 joules. But we already knew that because that has to be equal to mgh2, right? That's what we said in this right here. So it makes sense that this is the same as part C. All right, and then in the last part, they ask what the energy of the compressed spring is. So the total energy after we've compressed the spring. So at this point, we have the potential energy 1/2 kx squared, or k delta x squared. That's the total energy at this point. So it's not moving anymore. It's compressed the spring. It's come to a stop. Our velocity here is 0 meters per second. It's at a height of 0, so our total energy is 1/2 kx squared, this, the compressed energy of the spring. So because this is the total energy at that point, it's got to equal the total energy at our other points, right? So at right before it hits the spring, and when it's at a height of 100 meters, and we know that that energy is supposed to be 2.5 times 10 to the 6 joules. So this also has to be 2.5 times 10 to the 6 joules, just based on energy conservation. So this is the same as the kinetic energy in part D and the potential energy in part C.